Seattle-DAML. This isn't our first Seattle-DAML, but this is the first live stream Seattle-DAML. And I think we're on the air now.
Yes, we're on the
Fantastic.
air.
Hey, everyone.
So, hi everyone. My name is Alice, and this is
My name's Alex.
This is my co-host, Alex. So, welcome to tonight's Seattle-DAML meetup. We have this once a month, and tonight, especially, we have the pleasure of welcoming Ted Dunning, Chief Scientist at MapR, and he's an awesome public speaker, and we're really lucky to have him here today. Ted is going to give a talk about anomaly detection later. Alex is going to give an opening talk, a 10-minute spotlight on something that he's been working on lately. So tonight's event is sponsored by MapR and Microsoft. Microsoft is hosting the space, which according to some people has been a little difficult to find. So if you have friends who are on the way and who are lost, feel free to tweet about tonight's event or tweet directions out at them. The hashtag is SEADAML, SEADAML. And we're really also lucky to have Teriyaki Madness catering tonight's event with delicious food. There's tons of it. So eat up, drink up, listen up, and we'll get started. Thanks.
Thanks so much, Alice. Hey everyone, my name is Alex Corbinitz, and I'm a data scientist at Redmond. This talk, which is kind of just the opener talk, the opening band, if you will, for TED, is broadly about evaluating and comparing machine learning models. I'm going to talk to you about the practical problems of model selection in the context of machine learning-based classifiers, specifically, and how in today's literature, model selection is sort of glossed over, not really talked about too much in depth, but I'm really going to go into some of the practical concerns, looking at economic costs associated with machine learning models and looking at things like class and balance a little bit. Basically what I'm trying to say is that if you're using machine learning in practice, in an industry setting, you want your models not just to make sense, but dollars and cents. But before we dive in, here's a little bit about Remitly and me. Remitly was founded in 2011 to forever change the way people send money back home to their loved ones and their family members. And we're taking off strong right now. There's currently over $600 billion sent abroad in the form of remittances worldwide, which is about 4 times the total amount of foreign aid and nonprofits sent across the world. So that's a big chunk of money, and we're now the largest independent digital remittance company in the United States, which is pretty cool. We just announced our Series C in April, and we're now sending, I just queried this morning actually, over $1.4 billion annually around the world, and only growing from there. Something exciting happened last Friday. Our CEO, Matt Oppenheimer, just got named Ernst & Young's Entrepreneur of the Year, which is pretty great in the services category. So we've got good leadership and excited about what's coming. More about me. I'm working as one of 2 data scientists on our data science team at Remitly. Maybe one of you will want to be our third. If that's interesting to you, please feel free to come talk to me afterwards. Sounds great. I'm proud, born and raised Seattleite. Woo! How many of us here are from Seattle? Yeah, all right. I feel just proud of where I'm from, and always like to point that out. As Al said, I'm an organizer of DAML as well, and I've been a data scientist previously at another startup in Redmond called Nuku. Fantastic. So the agenda for this evening's talk. Just want to give you guys a brief outline, and I'll go quickly through this. We're going to talk about model selection and why data and fancy algorithms are not the only knobs you have when it comes to solving your machine learning problems. This is hard, and we've been finding that traditional approaches are inadequate. ML algorithms themselves have had a lot of academic coverage. Model selection problems haven't had quite as much of a focus. So this aspect is crucial for us in terms of delivering successful data science applications. A couple of these problems include the inclusion of economic constraints and class imbalances in the model selection process. The for us, there's a real penalty in being incorrect with our classifications. We have very high costs of misclassification in the form of type 1 and type 2 errors, for example. After that, I'm going to talk about how to address the economic impact of model selection, how to incorporate these different costs, just kind of at a high level. And then I'll touch on why not only this matters to us, but just emphasize that we're just getting started. As we like to say at Redmond, we're just getting started. We're not done yet. There are a lot of exciting things ahead of us. So you may think that in order to solve all of your machine learning problems, you only need to have big data. Or maybe you think all your problems will be solved with deep learning and neural networks, all these awesome buzzwords lately. Even Silicon Valley, the TV show on HBO, has been dropping neural networks and machine learning like it's nobody's business for the last few weeks, which I think is hilarious. But I will say, please stop fanning the flames of AI hype before another AI winter sets in. Thanks. So, like I was saying, it's not the case that you can use big data and deep learning to solve all of your machine learning problems. You really need to think carefully about model evaluation and comparison. So how do you do this for your use case? How do you evaluate and compare models in your specific setting outside of studying the theoretical properties of an algorithm? Today we're just going to focus on model evaluation in a supervised classification setting, specifically binary classification, in the context of fraud classification, just to give you a little context. So for us, big data is not enough. Not everyone has it, first of all, or maybe what you have isn't that useful. And fancy algorithms aren't a silver bullet either. The no free lunch theorem, as we know, tells us that there isn't a one-size-fits-all learning algorithm for any given classification task. So for all you deep learning people out there, beware, here be dragons. Model selection is tough. There isn't a lot of coverage in literature. It's a very practical problem, and it matters to us tremendously in our day-to-day work classifying fraud. So how do we do it? What do we need to incorporate so that we can improve the approaches we've been seeing thus far? It's not just about cross-validation, things like that. We're not just going to be comparing different classifiers endlessly and seeing which ones have the best performance. No, we need to have sort of an objective external standard by which we pick a model. Basically, we want to tie models into our business objectives directly. So in econ, there's this notion of indifference curves and utility. You may have a problem, like fraud classification, where the penalty of misclassification varies per instance. It's not sufficient to have, say, a loss matrix while training an algorithm so that you can weigh the penalty of misclassification higher for a different class. Each transaction instance can have a much higher penalty than another. For example, you may have transactions with several orders of magnitude higher send volume than another one. And so you can't have a single matrix represent the penalties across all of your transactions. So that's not really what we need to do. In economics, we have budget constraints and utility functions. Rational individuals, homo economicus, if you will, we like to maximize your utility by achieving the highest curve we can given our budget constraint. And so each point along this curve is equivalent in terms of trade-offs. It's called indifference curve, or maybe another term that people are familiar with would be a level set. Again, like I was saying, we have transactions, we have revenue associated with these transactions, but we also have costs. There's cost of review for reviewing a transaction unnecessarily, it's fraudulent, or that we think is fraudulent. And there's also the cost associated with missing a transaction that's fraudulent. And that's the highest cost of all. All right, so now that everyone's up to speed on economics, this is a confusion matrix. Confused yet? Models that have to predict a propensity score, such as logistic regression, have trade-offs. So it's not really one classifier. It's sort of a continuum of classifiers that you can choose as you vary your threshold of classification from 0 to 1. And what do I mean by that? When you have a model like logistic regression, you output a probability for your prediction. And basically, if you pick, say, a threshold of 0.5, you create a confusion matrix. Basically, you vary the threshold and you can create a continuum of different confusion matrices for your problem. So there isn't really only one that you have. When you're working with models that allow for you to make trade-offs, you have to think about which model gives you the best confusion matrix, if you will, for your problem. So we have to look at all possible confusion matrices that our model can help us achieve, and then pick one there. So how do we do that? Well, one of the classic ways is my curve is better than your curve. Therefore, I'm going to publish this ML paper and call it a day. This is the receiver operating characteristic curve, or ROC curve, which was originally used for detecting enemy objects in battlefields in World War II. It's pretty cool. This is one of the most prominent metrics for comparing and evaluating machine learning models. It's useful, it's impervious to class imbalance. It's common in the literature as well as in many fields like psychology, social science, and of course, machine learning itself. Basically, this dashed line, for those of you who aren't familiar, is the sort of x equals y line, and this represents what a random classifier would predict. So in other words, where the true positive rate on the y-axis would equal the false positive rate on the x-axis. One of the problems with this curve, even though I was saying it was a benefit earlier, is the fact that it ignores class imbalances. That's important for your problem. Another issue is that it ignores the costs of false negatives and false positives, which you may want to incorporate. Another very common and important machine learning metric is precision and recall. This is a little bit different than the receiver operating characteristic. We have recall, which is the same as the false positive rate here, usually on the x-axis, and precision on the y-axis. So recall you can kind of think of as, of all the positive instances, what proportion of those did our model classify as positive? Precision, the wording is different, and it's important that it's different. Of the positive classifications that your model has made, what proportion of your predictions had positive ground truth? And so this curve is sort of, again, just like the ROC curve, a set of trade-offs at which you can pick a point and determine the confusion matrix that would result from using that threshold for classification. So we haven't talked about cost yet. Let's do that. It's all well and good that one of my PR curves is better than another, but what if they're similar? Can I have a precision and recall curve or a ROC curve with worse area under the curve that actually suits my needs better? Generally we think, oh, the ROC curve with the highest area under the curve is the one I want. But I'm going to kind of turn that around and suggest maybe that's not what's right for you. Here's an example in ROC space. We've got two models, and we've got an indifference curve that we've created based on the costs of misclassification. So in each quadrant or confusion matrix, you have different costs. Your costs will define basically the slope and intercept of this line. And again, look at the orange one. The orange one has higher area under the curve, but the green one actually crosses our indifference curve. Why is this important? It means that this orange model is not viable for your business. It means that you may be losing money. Whereas the green one may have like lower AUC or worse predictive performance at thresholds below where it intersects with the orange predictor. But what matters is that it actually achieves thresholds in the space of this chart that are above your indifference curve. In other words, using thresholds on the green line here allow you to maximize your profit or expected utility, or whichever way you want to phrase the function with which you are computing these indifference curves. And I just want to make a quick note that indifference curves don't need to be linear. one other thing. Last in this talk, I'm not going to explore weighting training points differently during training or different resampling methods. These metrics that we're talking about with indifference curves are sort of post-training. Here we want models that output propensities so we can pick our own thresholds. And as mentioned previously, loss matrices during training do not work for our use case because of the transaction issues. So let's go back to PR space. We've got a machine learning metric that we've chosen to evaluate the predictive performance of our models. We've maybe got two models that we want to compare to each other and pick one maybe better or worse than another. We've got business costs, business objectives, constraints that we are subject to as a business, and we've got all those things together. Now, how do we actually pick a model? So here in precision recall space, we've got an indifference curve and two models. Note that the curve in red, which is your curve, has worse area under the curve in this space than my curve, which is the blue curve. But what matters is that your indifference curve here is pretty extreme, and all points to the right of that suggest that the red curve, which is yours, actually dominates the blue curve in terms of its maximum distance perpendicularly from the indifference curve. So that threshold is the point at which you are sort of maximizing the utility of your constraint. This is sort of the point you want to be picking on this curve based on your own indifference curve. So this kind of is counterintuitive when you are used to thinking about comparing models in terms of the area under the curve, or looking at one curve strictly dominating another in PR space or rock space. One thing to remember, if this is an approach that you're thinking of using, be sure to remember that business objectives and costs change over time. So you'll want to constantly recompute and reevaluate what these indifference curves look like so that you're sure that when you're training models and looking at the model selection process, that you're actually choosing models based on the current economic reality. Great, so precision recall and receiver operating characteristic are obviously not the only metrics that are useful or important or interesting when you are evaluating the selection process for your models. So I just wanted to bring up a really great talk that there's a link to in the bibliography. Sam Steengold gave a talk at the MLConf in Seattle in May that I thought was really awesome. He talked about different machine learning evaluation metrics, and there are 4 that are plotted here across their different ranges, basically to show you just how they behave. He talked about accuracy, which we're all familiar with, the F-score, one that he called Pearson's fee, which I call Matthew's correlation coefficient, which is a pretty balanced metric that works well with data sets that are balanced or imbalanced, and another metric that is called proficiency, sort of an information theoretic metric that helps you understand how well your model is explaining the information contained in the data set. So one interesting jumping off point from this talk would be to evaluate the notion of incorporating indifference curves with these other metrics in their respective spaces. So briefly, we talked about model selection. Data and algorithms aren't the only knobs you have. You've got a lot of knobs to turn in the data science process, and you can use other knobs such as your costs and your revenues to be able to do model selection. We talked about some of the problems with typical model selection processes. Some of them are just inadequate to help you out with solving all of the problems you need to solve. We looked at precision and recall and receiver operating characteristic and fusion matrices. We also addressed the economic impact of model selection and why this is important. Because if you have a model that doesn't even hit your indifference curve, you don't have a viable model. You need to keep going or reevaluate the model creation process or even the costs and revenues that you can achieve. Last This matters to Remitly a lot because we are operating in a pretty constrained space. We're in a very competitive landscape. We're price takers in that competitive landscape, so we can't adjust our prices very much. Our costs are high. There's an extreme imbalance in cost between the revenue associated with a successful transaction and the cost associated with a fraudulent transaction. So we have to be very careful about how we build models to classify fraud. So what does machine learning look like at Remitly as a whole? On the data science team, we're currently using machine learning for a variety of purposes, but here's a really important point. Machine learning applications are core to our business. Therefore, our business has to be core to our machine learning models. This is the driving force behind how we're doing model evaluation and comparison at Remitly. More specifically, we're using ML for a few other applications. As I said, fraud classification, left swipe on fraudsters, right swipe on great people. We're working on anomaly detection, stopping money launderers in their tracks. More of a marketing perspective, we're learning why users love using Remitly, why they keep coming back. Should we make changes in the product to increase retention and reduce churn? And last, because we're operating in a financial landscape, it's really interesting to look at movements in currency markets and see how that might affect demand of the app. So a lot of exciting things going on, and we're just getting started. So thanks so much, and remember that we're hiring for the data science team right now. Come talk to me afterwards if you're interested. Thanks so much.
Okay, so we'll pause for just a couple minutes while we get Ted set up. Feel free to grab more food, ask Alex some questions. We'll resume here in just a couple minutes.
Yeah. 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 I had to give a kind of a contrived example where the curves were really extreme.
How many guys are you?
70 of us right now. Yeah. We're so our team, the 2 data scientists, there's a guy above me, and we've got
All right, we're ready to get started with the main talk of the night. Thank you. Woo! It's really a pleasure to welcome Ted Dunning from MapR to tonight's talk. I was just chatting with Ted, and Ted has been doing data science since the early 70s, and he's been participating and contributing to the open source movement since 1975. So Ted has had a long and illustrious career and started out doing data science at Los Alamos Labs as a high school student, and did his PhD thesis on natural language processing, and worked on a variety of applications in the industry, in the insurance industry, and more recently, since 2007, on Hadoop, and since 6 years ago at MapR. So Ted is also a really wonderful speaker in high demand, and so we're really lucky to have him tonight. And his talk is going to be on anomaly detection, and we were in for a real treat. So thank you, Ted.
Thank you very much. I wanted to thank Seattle. It's a rainy day. I've had this raincoat now for about 6 months. I didn't know if it worked because I live in, this drought-parched part of the country. And so who could know if a raincoat was actually a raincoat or not? It does work. I'm really happy about that. Not only cool logos and bright red colors, but it works. So I'm going to talk about anomaly detection, which is really cool. Alex referred to that a little bit. Very often, you can't actually make a really informed decision of the form, oh yes, that's like this, I've seen those, or it's like that, I've seen those. You have to be able to say, that's not like what I've seen. That's an important decision as well. That's a single-sided problem. So we're going to talk about that. Now, I've given a talk on anomaly detection a number of times, but this one comes with new and improved algorithms. So you'll be seeing some new stuff if you've seen these slides before. And you'll be able to get all the source code for pretty much everything online. As she mentioned, I'm Chief Applications Architect at MapR. I'm also currently, my co-author is Ellen Friedman. She and I have written a book on anomaly detection. We've actually written 6 books over the last few years. It's gotten kind of out of hand. The only saving grace is they're all little. The goal is that they be 100 pages or so or less, so that they fit on one airplane ride. And that they talk about something where the world has changed relatively recently. So there's some very, very pragmatically possible solution to an important problem. We're not necessarily interested in talking about the latest research unless that latest research has led to a great simplification. We're not necessarily interested in just talking about the most amazing big data system, plug, unless that has led to a palpable change in how you solve problems. This second book in the series was about anomaly detection because we felt that as the scale has increased, very, very simple algorithms have come to the fore and made this sort of thing possible. So we're writing an entire series on these things. I'm going to talk about anomaly detection. That's useful. Well, we have a woman here who actually does this, works for utilities. Anomalies for those people are typically bad. Something is on fire or making bad smoke. Factories, not usually factories where people are sticking things. That's just a free stock photo I could find of kind of factory sort of thing. But factories that have machines building things or heavily assisted humans, because those machines can necessarily and easily carry instrumentation. Telecom companies are very, very interested in anomaly detection, not only because they can find malfunctions, but so they can find things like flash bombs. a concert in a particular arena is likely to overstress data links. They can bring online new bandwidth, microcells and things like that, but that transit usually costs them money. Or they can re-aim towers in the neighborhood of a flash crowd to give better service for the crowd at the expense of somebody else. They can also prioritize people in that crowd. So if you're a first responder, a doctor, or a fireman, or something like that, they can actually route your communications at a priority, even though the system's very much overloaded. So anomaly detection is useful for all of those sorts of things. It's useful also even for finding fraud, because the most odd things typically are not people who are doing reasonable things. The oddest things economically are very often fraud. So what we want to do is we want to discover rare events, unusual things. We want to find a problem before other people notice it. It's okay if we find and fix a problem before anybody calls in, and if they're always going, oh, I thought there was a problem, but no, it seems fine, then we win. If somebody else is finding it, that's a lose. The trouble is, and this is a huge problem, is we don't know what these problems that have never occurred will look like. By their nature, they are the things that we have not remediated in advance, because those are the things we imagined, and we probably have measurements for those. Those are not the extraordinary black swan events that we thought were completely impossible, because we thought those were impossible. It will be things that we cannot comprehend in advance. So how do we find those? Well, let's take a simple example. Here's synthetic data. See, data. I made this data myself. I used R. I feel like a data scientist. I sampled 10,000 times a normal distribution. Now, that you can get an idea. I mean, it goes up every so often. There's a little spike right there. But that's not really an anomaly. It kind of does that sort of thing every so often. Looks like an anomaly. Why would that be an anomaly? It's because we have a perception that normal is this, and that's weird. We've never seen that before. It's weird, it's bad, maybe. We ought to at least look at it. Now, sometimes we get that and that. Which one is the anomaly? Are they both anomalies? Are neither an anomaly? Basically what it is if occasionally we see the little spikes, then we say, well, that's not so bad. I mean, it should be doing this, but occasionally does that, but it does that. You know, occasionally the wheel squeaks or something. But whoa, that never should happen. Whatever our perception of normal is, the things that violate that are anomalies. And our sense of normal can be more sophisticated than just, it should be normally distributed. We can make a more sophisticated idea about that, but we have to come up with some idea of normal. Regardless of how sophisticated it has to be, we have to define normal before we can see anomalous. We're going to build a model, make some data, process it, things like that. We decide how far away something is, one sample, many samples, behavior, and then we can mark it as an anomaly. Now, there's a trade-off. So if I set the threshold here, I'm going to miss one of the samples. If I set it below that, I'm going to have a huge number of false positives. And we would like to arrange things so the high signals are all evil, horrible things, and we can do mathematically that if we can come up with a true probability distribution of the system as it should be, that inherently will give us the best ordering for this that is possible, so that any threshold marks the most anomalous things based on the definition we do. But there are always going to be trade-offs. We're going to have some false negatives or some false positives, or up here we're going to have lots of false negatives. We have to decide where we want to be. Now, traditionally people talk about this in economic terms, but with anomalies, we have a different sort of situation. We typically have a budget to deal with weird shit. We have a budget to deal with that, and so we might as well do is set our threshold to fill that budget. That's our alertness budget, however much we think we can afford to do that. So this is a little bit different way to do that. We should order things as well as possible, and then we should fill our budget for observation with the weirdest observations that we come with. So let's set adaptive thresholds. We know how many samples we're getting. We know what our budget is, so we can say we can handle 0.1 or 0.01% of the observations in our general purpose stochasticity observation budget. So if we can set our knob and calibrate our knob in terms of quantile, percentile basically, then that's the best way for our knob to be measured in a pragmatic sense. So we want action when something breaks, but action is expensive, and we don't want action when there is nothing. So we need to do this trade-off. And we need to really set it upper, lower bound, or lower bound if we want only lower bounds, or upper if we only want upper, according to percentiles. And there's a cool algorithm. I have to disclaim, I have a conflict of interest here, but it's called the T-digest. And what it does is you can take your measurement, you can put it into this little box, and it will, at the cost of a few kilobytes of RAM, actually keep an accurate histogram of the data. And it will keep more accuracy at the tails, where you care about accuracy. So the error is typically constant relative to the distance in quantile space to the end. So in the middle, like at the median, it might not be as accurate quantilely speaking, but at the edges, 99.99 percentile, it'll be part per million kind of accuracy. So it adjusts it according to the way you sort of want it. And so you can then set a threshold here at the 99th percentile, and you can just set off the alarm. So you can do that. It's available everywhere. It's super easy to use. You can use it independently of anything else. And so we're kind of done, huh? You thought it was going to be a long talk? Not really. Not really. Because you have signals like this. Where should I put the threshold? A and B are anomalies. You see that. Where do I put the threshold? Well, I can't put it here because I'll miss B. And I can't put it here because I have daily deluge of alerts. What I really need to do is just what you do when you see this. You go, oh, every day it goes like this. But woo, it didn't do the right thing there. We need a more sophisticated idea of what normal is. So we need to have some kind of model here that we subtract off of that signal. Subtract off that everyday whoop. And then the whole system, just like before, just like what we said, whoa, that sort of detector works. What about this signal? Can you spot the anomaly here? Not so much, because that's a heartbeat. I like those. That's not an anomaly. The other would be the anomaly. In fact, here it's kind of an anomaly. That's almost a skipped beat. You can find this sort of data online. There's beautiful samples of lots and lots of cardio data. What we want is a model of what's normal now. But it's now gotten to be much more sophisticated than just, it's kind of like noise this big, but it kind of does that sometimes. Now we need to see, oh, it's like this, and it has a downward, and then it has two little blumps afterwards. That's what normal is for a heartbeat. This is a much more sophisticated thing. We want a temporal model of the normal underlying shape, and then assume there's kind of normally distributed noise on top of that. So we could do that with heartbeats. Let's just window it. This is a windowing signal. It's a hump. It's 1 in the middle, and it's 0 at the edges. And so when I multiply times the original signal, I just get that. And when I move it, watch. If I move it over a little bit, I just see the beginning of this hump here. Move it again, now I see the end of that hump. And move it a couple things, oh, now we see this pulse. And so you can see that it's selecting out little pieces, characteristic motifs out of that signal. And if we take all of those and scale them, we can cluster them into a dictionary of the shapes of heartbeats. And because it's such a highly repetitive, kind of unidimensional signal, unidimensional meaning that there's kind of a trajectory that we follow in this electrical space of excitations as the wave propagates across the heart, but it really is kind of a circuit, which is very much like a line in some complex space. That means that we can use this sort of technique on it, and we can now reconstruct the signal based on the dictionary alone. And so what's left over is the part that doesn't look like a heartbeat. There's the heartbeat, there's the reconstruction, there's that doesn't look like a heartbeat. Now some of this is by nature, see that's a really steep signal, and since we only have a limited number of prototypes and we have fixed windows, our prototypes might have not have been exactly synchronized with how the real signal was, and so we get a little bit of a peak. It's not really normally distributed noise, but it's kind of like that. Here, notice something? Ooh, that's an anomaly. You can't really see it here, but you can see that it was unable to reconstruct that by using normal heartbeaty looking things. Here's a magnified view. You don't want your heart to do that. That's bad for you. It's the beginning of fibrillation. You die if that continues. And indeed, the system says that doesn't look like a heartbeat because it's unable to reconstruct it. So we've reduced a very complex signal now back to our first one-dimensional thing. You see the pattern. We're building a model. Oh, here's another anomaly. This is electrical. You really don't want your heart to do that. But indeed, the system cannot reconstruct that. It says, no way, no how does that look like a real heartbeat. And so the anomaly, the reconstruction error is huge. So we, again, have been able to do this. We built a model. We subtract away whatever the model says in a reconstruction sort of way. And then we're left this one-dimensional signal that we can then process with a variable quantile estimate. So we're seeing a pattern. A pattern. This is a model delta anomaly detector. The idea is building a model, reducing it to something like probability. The anomaly squared, if it's Gaussian, is the log of the probability. Now, log of the probability is really good because that gives us it gives us absolute guarantees that it's the best anomaly detector we can have if the probability we're estimating is real. Now, some people will say, as you saw on the slide that I accidentally flashed up on the screen, some people will say this idea of clustering is bogus. Can't do it. In fact, clustering of time series is meaningless. This is, people tell you you should have a bold title to a paper. There's a bold title. Eamon Gale says that his method is much better, and moreover, k-means clustering of time series is absolutely meaningless. But what he means is you don't get the same clustering every time. But we're not doing that. What we're saying is, can we get a model, not the model, not the ultimate model that is the truth of the universe. Can we get a model, any model that describes the universe? And if there are many, many, many models that all equivalently describe the universe, and finding some of them are easier than others, fine, let's find the easy ones, or any one of the easy ones. That's fine. So it's kind of a silly statement. I mean, he's right that you don't get repeatable things, but let's do some examples. The weakness of clustering is that what we're trying to do is we're trying to represent a space by putting little balls in there, little k-means clusters. And we're trying to say the signal is going to be approximated by the value of the nearest cluster. So the goodness of that would be if everything is close to some cluster. And if new data is close to some cluster in roughly the same way as old data was. Now, if that data is like the heartbeat, which is an essentially one-dimensional circuit in a high-dimensional space, that one-dimensionality of it means that a modest number of clusters can describe the data very, very well. When we do the dth root of 1 over k, so we have 500 clusters like we did in that other example, d is 1. The effective dimension of our data is 1 because it's one-dimensional data. So we're talking about 1 over 500 is the kind of error. So we should get good reconstruction. And reconstruction is all I care about here. I don't care about universality or repeatability. Just that when I train it, I get one reconstruction error, and when I run it on real data, I get something about like that. If, on the other hand, this is like 100-dimensional data, then even if k is humongous, we will have very large errors. So this explains why the k-means worked. So here's, for instance, synthetic time series. And there's actually a black line and a red line laying on top of each other. Here's reconstruction error. These are synthetic kind of magical weird pulse chains in a randomized system. And you can see we're reconstructing it. I did this so that I could exactly know what the original signal is, have no noise whatsoever, and then I could measure the reconstruction error depending on how many clusters. And indeed, the black is on my training data. As I increase the number of clusters, the error goes down, becomes very small eventually. And on the test data, this is data that I made up without letting the model see it, the error also goes down. So even though we were only training on 100,000 data points, therefore 2,000 clusters is absurd, we still continue to get better and better models. This is a case where k-means is working. Here's a case that's a little bit harder. I picked points randomly in three-dimensional space and then projected them by kind of a weird distortion-y thing into 15-dimensional space. They're really a three-dimensional surface in there in that complicated space. Now the k-means should discover that structure, and it should show errors kind of like we were just in three-dimensional space. It should give us the cube root of 1 over k. So if I have 1,000,000 clusters, it should give us kind of like 1% errors. If I have 1,000 clusters, it should give us like 10% errors. But k should increase and decrease the error. Now we have a little bit more change to the held out data because we have more degrees of freedom. We have lots of dimensions here. But here, I'm going to look just at the black one, just the training error. The training data should be able to be expressed by the clustering about a cube root of 1 over k. And here's a cubic model. So sure enough, it fits. So that's the explanation of why the clustering works. It's low dimension, in fact, even though it appears to be very high dimension. So that's when that works. But we can go much further. We can build much more complicated, much cooler autoencoders. That's what these are. You can use deep learning. You can use neural nets. You can build more sophisticated things that don't just do little balls, do entire sheets through this space and approximate it that way. And you can get much more powerful autoencoders of this sort. So that's the autoencoder I get. Now, that's nice. That's really nice. But there are very, very different kinds of data out there, too. There are things that occur at times, and the times are random, but the event is just the event. There is no magnitude associated with it. Imagine clicks on a website, page loads. There's no correlation between you and her and me and him. We come at our own times, and so every page load seems disconnected from every other. And it's not a continuous time thing. We're trying to predict that. This comes from work I did when I was at Music Match. And what the problem was, we had a new kind of a hyperactive CEO. And what would happen is he would call up at 2 in the morning and say, Ted, we haven't had any sales in 15 minutes. Do you think there's a problem? The answer, of course, was, yes, there's a problem. My CEO is calling me at 2 in the morning because he's freaked out about whether or not we have sales. that's a problem. Whether or not it's a problem that we haven't had sales in 15 minutes, I have no clue, because I'm still asleep. So the problem was to fix that. We needed to get to where we found all of those before and build a system so we get the alerts first, and he has a dashboard that he can look at or not, and it turns red 10 minutes after our beeper goes off. So now he can answer the question himself, and when he does call, we go, Dennis, where you been? We're on this. We've been here. Eventually, if you do this right, your CEO will learn to sleep through the night. This is important in their maturation and also important if you want to build a company. They should not be waking up in the middle of the night just because they're worried you might have screwed up. That's really bad. So let's talk about how to build this. The basic idea here is the time between events is the key parameter. If our data is totally random, totally uncorrelated, then time between is the crux, statistically speaking. The count over some time period is a disastrously bad number to look at, unless you have very high rate events. The reason it's bad is because either you have a short time interval, in which case your counts are tiny and your error bars are huge, so you can't decide anything, but you can decide nothing quickly, or your time intervals are long and your error bars are small, and you can make decisions, but it takes a very long time until you can. Either of those is bad. I mean, there's an inherent problem there that making decisions quickly has a higher error rate, making decisions slowly is slow. But neither of those is good. But windows are one of the worst ways to process the data. Processing it as the time since the last event, time since the fifth most previous event, is a much better way to go. And so let's take a look at this. Let's take Poisson, random stuff, just exponential inter-arrival times, and we want to alert as soon as possible on loss of signal, loss of this pulse train. We just look at the time between intervals. That's what I plotted here, the time since the last event. And of course, that goes up until the next event arrives, in which case this goes back down to 0, goes up again, goes down. It doesn't show it going quite back down to 0 here, just because there's limited resolution on the plot here. Here's the 99.9th percentile, 99.99, and indeed you can see these 1,000 points don't cross that, and they certainly don't cross that. They seem to have a very nice disciplined nature to them. And even more than that, this time is the log of probability, which we showed a little while ago, or at least I claimed with no proof whatsoever, but great moral authority, that that is the best detector you can build. So for this kind of signal, for finding loss of signal, the time since the last event is, in fact, your optimal detector. It will detect things as fast as possible with the smallest false negative rate and false positives. But unfortunately, the real world isn't just like Geiger counter noise forever. It looks like this instead. If these are the inter-arrival times. Notice the times go really high at night, and there's a lot of short times during the day. Now this is a little bit like our original problem, where we had that, but we can't subtract away stuff here because we just have these discrete measurements. We can't subtract something off there. But if we can estimate the average rate, now this is synthetic data to make a pretty picture, therefore I know what the true rate is, so I can draw a really pretty picture with the actual rate on there. But if we divide the inter-arrival time by the rate, we get this. Well, we get this, which looks exactly like our original stuff. These are the same numbers as before, but divided by that rate. Because if this is the inter-arrival time with Poisson stuff, then the log of that is the rate times the time. So this is pretty cool. We can adjust those numbers that were so variable simply by estimating the rate well and dividing by it. And that gives us beautiful data These are 100,000, no. Yes, 100,000 data points, 10,000 data points. About a dozen are between 99.9% and none of them are above 99.99, except one's close. So yay, the numbers kind of work out. But the point here is that this inter-arrival time as scaled is a perfect estimate. Here's another measure. The white lines that are completely and perfectly superimposed by the pink are the theoretical distribution for this statistic, and the pink are the actual. So instead of subtracting like we did before, what we have is we're going to be doing a subtraction, but in log space by multiplying times an average rate variable, or dividing by rate. This is an average time measurement here. So if we have a rate predictor that produces this lambda based on some rate history, then we can make our t-digest do the same thing again. The key now is just build a good rate predictor. So here's some real data. This is Wikipedia's main page, and I've got a gray line behind it, which is 1 week delayed data, trying to build a predictor of this. Now this is November 2008, so you can see right here, this is Thanksgiving. Looks like everybody sits down around noon and they stop looking at Wikipedia. I would have guessed just the opposite. I would have thought they'd sit down and start arguing about something that's in Wikipedia and all start looking at it. So maybe that's when they start cooking or something. But whatever it is, you can see that 1 week delayed data is not a very good predictor. Well, it is a great predictor most of the time. See, it predicts Saturdays and Sundays are odd. But then when something weird happens like Thanksgiving, it becomes poor. And here's a worst case. This is the traffic for the Wikipedia page for Christmas, for November, December of that same year. Well, obviously, kids start looking up Christmas, apparently over and over and over again. And then on the day before Christmas, they go nuts looking up Christmas. It's like, what's going to happen? Same thing as last year. Calm down. But the 1 week ago predictor becomes just abysmal when we get seasonality effects like that. So we need to do better. So we need a better rate predictor there. Now we can predict the log of these event counts. That'll give us, because we talk about ratios a lot. We talk about percentage improvements. So logs are very natural predictor in here. And also, as the data scientist, I told you that's what we're going to do. That's often the way the argument goes, just like, let's just get on with it and move along. I've done this before. And if the model works, then the argument didn't matter. If it doesn't work, then I grovel. I've done that. So let's let the model look at many values, not just 1 week ago, 1 hour ago, 2 hours ago, 24 hours, 25 hours, 48 hours, 49 hours. That'll let it get some of that history. We'll use an L1 regularized linear model. Got to say that really fast so everybody thinks you know what it is. It's just a model that doesn't like to have parameters. And so it's going to try to squeeze as many to 0 as possible. And what we get then, here's the current rate, 1 hour, 2, 3, 24, 48 hours ago. We're going to predict the log based on the logs. And here's how our model does. We trained it on November, and here it is tested on December. So already the rate has doubled on these days, and you can see it's tracking within about 5% almost all the time. That's pretty cool. And then it drops again on the weekend, and then it crescendos. And even on Christmas Day, the errors are about 30%. The day after Christmas, when traffic crashes, errors are again about 30%. But this is about as bad as it gets for rate predictor, where you train on November, and now you have to predict ahead for December. This is pretty cool. This means that we can build those anomaly detectors, and our CEO can learn to sleep through the night. Now, some days this magic works. Some days we have to find another one. So I'm going to show you a case where exactly the same thing, timing, inter-arrival times, doesn't work. And I'll show you why. So this did work for website visits. It works fantastically well for that. When we want to say purchases have stopped or something like that, transactions have stopped. Something's broken, we'll go find it. But here, suppose we have some microservice sort of thing, and we're sending streaming messages. So messages come in here, they go out here. And suppose that we have metrics and exceptions coming out. So the timing analysis that we just did is going to work like gangbusters on the exceptions, because those should be very rare. We should know that if we start seeing 10 per second, something broke, typically upstream, because it's never our fault. But the metrics are really more interesting. Here, suppose I'm going to inject a fault into this thing, and we'll see what we can see. We want to detect more than just the cascading things stopped happening sort of case. We want it to detect misbehavior, more subtle. So the arrival time stuff. So here are inter-arrival time statistics for the messages leaving the thing we're testing. The fault was injected here. And you do notice that we kind of have a fair number of out-of-bounds things there. There's kind of a weak indicator that there's a problem. This is the 99.9 indicator. There's about 1,000 data points in here, 1,000 here, 1,000 here. And suddenly, way out here, we're starting to get a few samples up there. This is where the data generation stopped. And so, of course, we start seeing less data come through. But it's not a very strong indicator. And this is an egregious fault. Here's arrival time, start of processing versus end of processing. So you can see that fault started here, and what's happening is our response time just going to the dogs. Something really bad has happened here, and it's gotten progressively worse and worse. And yet, we can hardly see it with those inter-arrival times. That's because about as many things are coming as ever, and so the time between the things leaving is not increasing very quickly. But here's a way we can do it. We just do a systemic model, say there's something about this system that should be modelable. Like stuff comes in, that thing comes out. So here we could build a model based on that response time, and here's what the response time does when the fault is injected. We would find it, it would be an egregious fault output, and we can correlate them. Then we can find that fault. So again, we can model, we can build these models, we can detect it. Anomaly detection, classification are also a useful pair. If we start seeing certain class of anomalies, once we've seen 50 of them or 100 of them, hand them over to this guy. He'll build a supervised model. It won't be an anomaly anymore. It'll just be kind of a rare part of normal. Now we go back to our regularly scheduled, find the really weird things. So, anomaly detection is best done with a probability model. There's a number of ways to do that, but minus log p is the key factor that we need to look at. It makes things easy to understand. It lets us turn knobs in quantile space, and that lets us make budgets happen in real world. Simplistic normal distributions are just not feasible, but it's not that hard to build these models. You saw, I was doing like did by an estimated rate, and a rate is just a linear combination of previous rates. That's not really PhD work. That's a really simple model. And we can adaptively set the knobs so we can get good detections of these systems. Different systems, different strokes, different models. We can do continuous time series. We can do cooler continuous time series, more than a Saturday afternoon of coding sort of thing. But these are not super hard to build. We can go more on to events with times on them, events with colors on them, events with money on them, labels. Who did you do the business with? How much did you do? And we can find anomalies in all kinds of places. So there you go. Model, find the difference, turn the knobs, and there you go. We got a book on it. The book doesn't have all of these, but you can find the code for all of this, and you can get all of the books online for free. We have recommendations, anomaly detection, time series, big data applications, a very cool way of hiding data, and a book about common forms of streaming architecture. Oh, he's got a book. He's got the Pony book, the very first one. It's called the Pony Book because there's a pony on the cover. None of the others had that distinction. None of the others had ponies or anything that cool except the stream. That's a rejuvenated river through Seoul. So you see, they used architecture to make a stream work better. It was really kind of cool. Was kind of cool. It's not as cool when you tell it to other people, but it's the way puns are. Thank you for coming. We got time for questions. You can find slides and other related materials here on our website. Pause for all the iPhones. Mine are iPhone delay. There's also a bunch of things that you can get from MapR. We have free training, free discussion groups, and all kinds of stuff that you can get there. Thanks. About the right time.
Yeah, perfect.
Okay,
We
good.
have time for questions.
Could you you're working with the signal, could you directly apply signal processing techniques, for example, moving things in the time domain and such?
This is all signal processing. Signal processing is kind of where I started. I was an electrical engineer back in the dark days. And this is all signal processing in drag, in much more stylish terminology. That's all it is. So almost all of this is time domain oriented signal processing. And you know, when you're talking about anomalies, you're very often talking about things generating data, Internet of Things kind of stuff. Maybe you don't have the internet part, but you almost certainly have the things part. And things are naturally embedded in time. And if you're measuring stuff, if those are signals, it's time analysis, time series analysis of signals. So, yeah, exactly what you say. Just tell anybody to get scared of it because it sounds so complicated. It used to be complicated. It used to be really hard, but now a lot of this is really easy. It used to be much, much harder. Partly because, you know, the computers were just dirt back then. Any other questions? I won't necessarily empathize with other questions quite that much. Yeah.
I wonder if you could fight back against the objections of those two folks.
Could I fight back against the objections?
Yeah, I wonder if you could use either an idea that comes out of neurobiology and also out of computer vision, where you adjust your signal to a standard position. Like with SIF features in vision, you automatically orient it so that the position, the pose of the object doesn't matter.
Yeah.
In neurobiology, in neural signal processing, you've got this thing called a spike triggered average, where it's just like you're triggering an oscilloscope, you trigger on the leading edge
I'm
of
gonna
the spike and you move that to
Yeah.
the next position.
I'm going to summarize this for all the people who can't hear you. But you're talking about taking benchmarks and reference points in a signal, and then you can look from that time. And yeah, you can do some of those things. And that's essentially what the heartbeat analysis was. It was picking what appears to be the benchmark time in there and looking at differences from that point. So it was doing a little bit of that. But I think that we, you know, to some degree what you're saying is we could find a meaningful and universal truth there if we just benchmarked and went to the right reference point. But what I'm saying to them, when they say clustering is meaningless, I kind of respond a little bit more zenly, like, who needs meaning? You know, did we really need an absolute? Or is a subjective truth that it works good enough? And to me as an engineer, trying to build a thing, that it works is the key measure, not that it is true with a capital T. And so I reject their entire argument. The fact of the argument, I reject. I will not argue with them. I just say, whatever, dudes, that's not what matters. And so, yes, benchmarks can be very good if they exist or if we can find them. But in a space of trying to find models in 100,000 dimensional space, it's very hard to find references or even define what angles mean. In a visual field, we have a two-dimensional temporal signal. Referencing is so much easier because we know what angle means. But in the space of finding all models, we cannot do that. We do not know what truth is. we can't even define what it would be, could we find it. And so in that sense, the only truth I admit for problems like this, does it solve my problem?
I don't think I'm talking about finding what's true, but merely shifting it into a position.
A congenial set of axes. Yeah, congenial axes are very important for many problems, especially in high dimension. The great example is you just take sample corners of a cube. And if you project those on the right axes, it looks like a square, obviously, because that's what a cube looks like when it's projected. But if you pick a random set of axes, it looks like mush. And it's very, very, very hard to detect those correct axes. But for k-means in particular, there's lots of good answers. And there is no single good one. We don't need to do orientation. Yeah.
So speaking of k-means and high dimensions, I was just thinking about your example where you sort of projected points in R3 into R15, and the reconstruction error wasn't so bad using k-means. So my question is, if you have a situation like that where you may not know the underlying data really lives in sort of a three-dimensional like subspace of your space of data, do you guys think a lot about dimensionality reduction techniques to apply before you do clustering, or do you say, hey, this k-means does a good enough job on its own, we don't need to worry about it?
So the question is, do we do dimensionality reduction on the presumption that there's a simple space that this data comes from? Well, if that were true, that would be grand. I make no presumption. But the clustering is itself just such a simplifying projection. It is diagonalizing the space. Now, it is doing that by projecting 30 dimensions, or 15, up into 2,000 dimensional space. So it's a little bit like a kernel tray, in that it's putting it into a higher dimensional space, but it's putting it into a higher dimensional space so that the simplified structure becomes apparent. So it is itself a simplification type of technique in that the data becomes very, very sparse. Which is the closest cluster? It becomes binary, and only one value out of 2,000 is true. So it's now suddenly very simple data. And so modeling systems work against it very, very well. But it's a different kind of simple than reducing it by some linear or nearly linear transformation to just a few variables, where by nature the true nature of that relationships have to become a little bit more elaborate. So it's just the opposite, but it's still the same idea behind it. Yeah.
So I have a question about defining what anomaly is to at a given time. So with changing time, say if something appears to be an anomaly today, might not qualify as an anomaly because we haven't seen the data for tomorrow. So how do you really change your definition and thresholds with more data that you get in, and where should you have that flexibility for adjusting for changes?
Well, as an amoral engineer, I have great flexibility because I have no beliefs. And so I merely say an anomaly is what I haven't seen yet, not what should not be, or what is, vile somehow to the true nature of things. I merely say, wow, I haven't seen that before. Now, when I say I haven't seen that before, I have to have some way of saying it is far from what I have seen before. So I must build some simplification, not just a catalog of a literal memory of everything I've seen. I need to build some simple description of what I've seen so that I can look at that and say, this doesn't look like that in general. But I make no great philosophical claims other than what I have seen. And then can I describe what I have seen economically to myself and in such a way that new data seems to fit it, then I'm happy. And then if new data doesn't fit it, I call it an anomaly today, but if it occurs a lot, I will incorporate that into my perception because I've seen it. So I'm very flexible that way. Tomorrow I will have seen new things today, and I will have a new idea of what an anomaly is. Which is a depressing point of worldview, but at least I can get some things done. Yeah?
Could you go into more detail on how you see k-means applied? And by an example, I in the past have used it in much the same way you said for the SIF, where I'll take my data and I have some new data. I want to see if it contains an anomaly, so I will take old plus new, and I will build some k-means to build clusters, and then I'll examine those clusters. And if I see that there are clusters containing only new data, then I think, hey, the k-means describes a model, and my model somehow has changed.
Yeah.
So that's one example of
So,
the
so,
deep
so
conversation.
using a k-means on new and old together presumes you have the new already. And finding clusters with new data only is prima facie information of change. But you could have seen that change the same way if you had clustered only on old data and looked at the distance to nearest as the anomaly signal, is suddenly you would see a hike in that when all of this new cluster appears. It wouldn't be in a cluster, meaning it would be far from a cluster, and therefore the distance to nearest signal would take a jump. And so you could do it by clustering both old and new together. That's great if it's all really old data, and you just are making an artificial separation of new and old. Or you could do it in a streaming way.
And your streaming way is much less expensive.
I wouldn't call it less expensive, I would call it less need for a time machine if I'm trying to actually look at new data that I have not seen yet. All I can do is cluster the old data unless, my friend from 3 years from now tells me what data is. And so I make the old clustering, and then I can adjust that on the fly if I want. I can do streaming type clustering. But then I can always be looking at the distance to nearest as my anomaly detection. And that will give me the same thing you're looking at, except I do not need to be able to cluster in prospect, only in retrospect. So it's the same technique. And I also, I used it here, I mentioned it like 50 times, but the only virtue it had here is that I had one Saturday afternoon to code this up. And I could do k-means for sure. Now there were k-sparse techniques, which is kind of like overlapping clusters, and I could have used deep neural nets, could have used recurrent nets. I could have, would I get them done on a Saturday afternoon if I'm not using those tools every day? Nah. I would have been reading the documentation the whole afternoon. Whereas k-means I could just do, and I could find a signal that made it work. And so that was its true virtue here, is that it made the point you can build a model. Not that it's a universal model builder. We saw that as the dimension of the data increases, it becomes increasingly bad. Just good for signal-like things that exhibit circuits. Lorentz attractors, for instance, would be killer with k-means. But strange attractors in general have low dimension, and so those would all be fine. But that's not a great claim to philosophical greatness. There's other ways to do this, much better ways to find a manifold in general, but it's super easy. And I'm cheesy, and k-means is implemented in R, and I have it in Java, so you do what you got. And then it worked, and I was done. I got to eat dinner, so not bad. Could be. Nobody from there has asked a question, which tells us, there's another kind of thing that you can use k-means for. And I've done this with telecom data, where you cluster where everybody's reported, and you look at the rates for different regions, which were just anomalously happen back then.
Question, how long did it take for you to retrain your former CEO about anomaly?
It took about a week, 2 weeks. Once he was wrong 5 times. The trouble before was not that the real ultimate, you look at proximal cause and ultimate cause. The ultimate cause of the problem is that he would call me and I didn't have an answer. Once he called me 5 or 10 times in a row and I had the answer ready, then he very quickly reset. But as long as it was like half the time he was the first one to find it, he felt like he had to wake up at 2 in the morning. And it's not an unreasonable inference at that point. Which is we need to step one further back and say, what was the real problem? It wasn't him waking up. It was me screwing up and not knowing about these problems before he did. So we just have to always think back a little bit until it's on us. Then we can fix it. But he was very quick to change. Yeah.
So, are you modeling?
Speak loud.
Okay, so for the purpose
and for e-commerce website. So I have this module here, and state is the data, all the data. I think this is purchase market is calculated. But then there's the signal comes. The signal comes for the credit card or for. So this is the thought. And then how quickly you can immediately retrain your model to once you catch a signal, you know this is the thing. So this is good, and then this is the thought, and you catch this from now on your model.
So the question, how quickly can you retrain models? Well, you can retrain them very quickly, but if you retrain them very quickly so that they make big changes quickly, then you may be chasing noise.
Yeah.
And so in all of this, there's a thing very much like Heisenberg, where if we want an answer quickly, we must accept higher error. And if we want a more cautious, longer-term answer, we can get a more precise answer, but it will be late. And so all of this time series type analysis has that problem. If we try to determine the frequency of a signal, if we do it quickly, we have high error. If we do it a long time, it takes a long time. If we want to change to new patterns of fraud, we have to be very cautious. The slowest part of that is us understanding something has really changed. And with models that deal with financials, the cost of putting out a bad model can be very, very high. And so we have a bit of caution about doing that. And that caution is good and natural, and we must have that caution. And so that's the slowest part. The numerical part is we can do very fast, but the pragmatic, cautionary, fiduciary responsibility part is often the slowest part. If you have a legal certification on a model, if you have to prove that you tested it before, all of that will slow it down. Now, that said, there are optimal ways, not in this talk, but there's another thing called Thompson sampling or Bayesian bandits, which will make a decision between models or regressions or infinite numbers of choices even in the theoretically optimal amount of time. So they will give you low accuracy decisions fast and high accuracy decisions slow all at the same time. And they will minimize, they will give you soft decisions as well. And they will also tell you how much money you leave on the table by making a decision now. And so those are extremely valuable techniques when you have to know that you are making decisions as fast as possible. Those, if you can get measures of what the cost is, then those will help you make those decisions. And Bayesian bandit is the best search term. You'll find my blogs on it and other people's blogs on it. That'll lead you to the full-scale literature and the sample code that I have online. I have a cool video, but that'll be another talk. So, well, thanks. This has been a great audience. You know, the best part is always the questions, because that's what makes a good talk, really. And the part before is just to stimulate questions. Thank you very much for coming.
So we have the room until 8:30. Feel free to stick around, chat more, ask more questions. Please eat more. Take food home with you. And you can, again, tweet about tonight's meetup using hashtag #CDAML. And please join us again next time.
Thanks, everyone. First live stream. Ooh.